Good day to you, pre-calculus students. Hopefully you had a great Thanksgiving break as we approach another topic regarding polynomials. We're going to do 3.4, which are graphs of polynomials. You're going to see some things that you've already looked at in a way, but now we're going to put this puzzle together and how to graph a polynomial, how to look at a graph of a polynomial, maybe even write the equation of it. Let's get started. Your objectives, as usual, I put them up there for you to see what kind of things we're going to do. We're going to recognize characteristics of graphs of polynomials. We're going to use factoring to find zeros of polynomials. Those are your x-intercepts. We are going to identify zeros and their multiplicities, because when a function looks like a roller coaster, I'll just do a fast little sketch of it. When a function looks like a roller coaster, it knows what it's doing. By the way, that's a pretty smooth curve. There's no breaks, there's no points. Let's call that the x-axis. This particular polynomial has a zero here, 0 here, 0 here, 0 here, 0 here. So since there's 1, 2, 3, 4, 5 zeros, this could be a fifth degree polynomial because there's 5 zeros. And it can have, a fifth degree can have 5 real roots, and those are real. And another one could look like this. Let me show you another polynomial. Okay, it's a little more exaggerated, but let me see. I have a 0 here because it touches the axis. I have a 0 here because it crosses the axis. Then I have a 0 here, but look at how wide the base is of this loop. It's still a smooth curve, but it rode the axis for a while. So what happens is this one bounces off. So that means whatever x that is, there's 2 of them. That means multiplicity of 2. This one, since it only crosses like a line, there's only one of those. Whatever x that is, whatever x that is, there's 2 of these. And since this one takes up a lot more space on the x-axis, there could be 3 or 4 or 5. Well, it can't be 5. It would have to be an even number because it does bounce off and doesn't cut through. If it's an odd number like 1, this one right here is only one of them. What did I write up here? That was, maybe I said something I shouldn't have. There's 1 right here, and 1's an odd number. This could be a 3, or it could be a 5. There could be 7 of the same 0. That's what multiplicity means. Okay. We're going to look at end behavior. What does it do in the future? What did it do in the past? Well, in this case, it fell from the future, and it rises. It falls. It's coming this way from the past, and then it rises this way. So it's past and future. That's end behavior. Either way, we're going to infinity both sides. As I approach left, I go to infinity. As I approach right, I go to infinity. Then we're going to understand the relation between the degree and turning points, which I think we've already discussed that, so that'll be easy. And then we're going to graph. We're going to look at graphs, and then we're going to use something called the intermediate value theorem. Let's start on this one here. We're going to recognize characteristics. So as I look at these 2 graphs, what characteristics do I see? Well, very similar to, they're both similar to each other, they're the same picture, but what I need you to see, there's a difference. The first one is a polynomial. because it's a smooth curve. Smooth curve goes forever one way, then it's very smooth, no points, it's very smooth, rounded, and it keeps on going. So we say this is continuous. If you read this paragraph up here, you'll see the word continuous. It's continuous everywhere. So that means it's continuous from negative infinity all the way to infinity. That's a polynomial. It's smooth curve. It has something called turning points, that it changed the direction. It was increasing and now it's decreasing. Now it's still decreasing, but now here's another turning point, it's increasing. So those are turning points. And then it goes forever, straight up forever and ever and ever. And to the left, it goes down forever and ever, down and to the left, up and to the right. This one here, see the difference here? What do you notice? It broke. So because this piece doesn't go forever, it stops right here, and then it picks back up and goes forever, this makes it not a polynomial. Yes, even though this is still smooth and still got a nice little turn here, and then it's still smooth and nice turn here, the party stops right here. So no more is this a polynomial. Sorry. That just, if you read up there in that what I circled, you'll see that this is not a polynomial. It's not continuous. If it's not continuous, it can't be a polynomial. All right, example 1. Just identify which of these are polynomials. Look at number 1. It's not labeled, but it's the first picture. It is smooth. It goes down and left forever that way. Very smooth as you climb. It goes up and it rounds nicely. That's a turning point. Very still smooth. Not picking up my pencil, never picking it up. Still smooth. Not picking up my pencil, still smooth. Nice curves, and it goes forever. That's a polynomial. Look at the second one. Yes, it's smooth, and it does go forever. It is continuous from negative infinity for sure. Then if I keep on going, look at, it keeps going after I turn. So it is continuous, but it's not a polynomial. Why? That's not a smooth curve. That's a sharp turn. Polynomials do not have sharp turns. You might remember that picture as an absolute value function. Absolute value, f of x, here's the parent, is not a polynomial. What do you think about this third picture in the bottom corner here? You're right. It is a polynomial. I don't see anything wrong. Look at the last picture. It's not a polynomial. It could be considered a piece of a polynomial, but it's broken. So I'm going to stand by my decision that it's not. Of course, I've been wrong before. You can look at the answers and see if we're right. I think I am. Okay, let's use factoring to find zeros. Factoring to find zeros. And there's a few simple steps that they would want you to do. Set your function equal to 0. And if a polynomial is given in factored form, that means it already is factored. That would be like you see something parentheses, something parentheses, something parentheses, with maybe, who knows what could be in there. Could be, let me change the color here. Could be an x plus 1. Could be an x minus 2, x minus 4. You see the point? That could be my function. It's factored already. And for that matter, you could also see it where one of those was repeated. So there's two of them. So maybe there's two of those. So it's squared. That whole factor is squared. That's wonderful. That makes it so easy if it's already factored. But sometimes we have to it's not already factored. We have to factor out any common monomial factors. What does that mean? Factor out common terms. And then what's left, hopefully we can factor it. Hopefully it's a square, quadratic. Those are a little easier. Then what you do is you set each factor equal to 0. So I would say x plus 1 equals to 0, x minus 2 equals to 0, x minus 4 equals to 0, and you solve them for x. So in other words, the first answer would be a negative 1 because you subtract 1 from both sides. The second one, I'd add 2 to both sides. The third one, I would add 4 to both sides. So that's what we would have to do. So let's do example 2. It is not already factored. So you are forced to factor this out. Now, step 1 was look at every one of these terms. Is there anything in common that we could pull out? I hope you notice it, that I could pull out 1x for sure. And if you look carefully, if I pull out 1x, I would still have 1 left here. So I can pull out 2 x's. So what we do is we rewrite this. We say f of x is equal to pull out x squared. That leaves me, when you pull out x squared, that means I'm pulling 2 x's out of 6 x's. So you're left with x to the 4th. Remember what happens if you were to go in reverse and multiply this together. X squared times x to the 4th, it means keep the x and add the exponents, 6. Well, that's what I started out with, remember? So I know I'm right. I pulled out x squared, I'm left in x to the 4th. Now for the next one, if I pull out x squared, I still have a minus 3. But if I pull 2 out of the 4, I'm left with x squared. Then the last one, if I pull out x squares, these x squares will go away. So I'm only left with a plus 2. Now, remember, if you were to distribute it back like I just started the first term a second ago, if you were to go and distribute, it'd come back to the same problem. So that's why these two things are equal to each other. This problem is equal to this. But why do I like this? Because I can factor this perhaps. And trust me, I can't always factor everything out. Sometimes I get lucky and I can factor. In this case, I'm going to keep the x to the 2nd power. And now I'm looking at how do I factor this? Well, most of you probably don't remember. But if you have a 4th degree and the second term is half of it too, then I can just pretend that I'm pretending. I'm just going to pretend that I'm looking at x squared, and half of 2 is a 1, minus 3x, and then I keep the plus 2. That's what I'm pretending to use. So if I can factor this into 2 binomials, and I realize that there's a 1 in front, so that means only an x times an x. The first times first will give me x squared. So then I have to look at here. Look at this 2. Now technically, I look at the 2 and I look at the 1 and I multiply together and I get a 2. And I ask myself, what 2 numbers multiply to get 2? Well, your choices are only a 1 and a 2, or a -1 and a -2. That is the only way you can create a 2, by multiplying 2 numbers. So the question is, which one of those pairs do I choose? Since there's -3, I'm going to take this set right here, because if I add those together, -1 plus, I'll write that out, negative 1 plus a negative 2 is a negative 3. So I take a negative 1 here, and I put the negative 2 here, and it doesn't matter which one gets it. Now, that's how I factored x squared plus 3x plus 2. But remember, it really wasn't x squared. It was an x to the 4th. So in reality, what really happens, guys, is x squared stood for x to the 4th. That means this x really stands for x squared. See that? An x squared times x squared, if you use FOIL, is x to the 4th. And then so this minus 3x, well, it's not going to be affected because I'm still going to put minus 1. I'm still going to put a minus 2. So if go ahead and FOIL that out. FOIL that out and see if you get x to the 4th minus 3x squared. You will. Well, okay, anyway. So this is still f of x now. This is my true f of x, factored correctly. What do I have to do? Set each term equal to 0. So I say x squared could be 0. X squared minus 1 could be 0. X squared minus 2 could be 0. Well, that's easy. X squared equals to 0. If I square root both sides to get rid of the there, and I use plus or minus always, I get a plus 0 and a minus 0. Well, that just means 0. But there's two of them. Just keep in mind, there really are 2 zeros. So you're going to see that it probably doesn't cross the axis at 0. The function would probably, that's a whole other story when we get to it. This one, add 1, x squared must be 1. Square root both sides. Don't forget to do plus or minus this side. Again, I have 2 answers. I have x is equal to a positive 1 and a negative 1. Oh, that gives you 2 different zeros. Let's do this one here. Plus 2, x squared is 2. Square root both sides. Square root, do plus or minus. X is plus positive square root of 2, and x is also the negative square root of 2. There's 2 answers. So this particular polynomial has 1 real 0. I'm going to circle it in green, or box it in. 1 real 0. I'm going to go here. I'll just list them out. Zeros. We have a 0. We have a 1. We have a negative 1. We have a square root of 2. We have a negative square root of 2. 1, 2, 3, 4, 5. And you're thinking to yourself, wait a minute. Didn't you say earlier that if there's a 6, there could be 6 real zeros? Yes, because there are. Remember, there's actually 2 zeros that come up when I square root it. It's actually a positive 0 and a negative 0, but it's still a 0, so it doesn't really affect anything. There are my zeros. Now, I'm thinking about the open math assignment you guys did the other day, and I was so proud of a lot of you guys. I was very proud that you figured it out, that when you keyed in the answers for the intercepts, the x-intercepts, it marked it wrong. Because sometimes they don't want you to say, here are my x-intercepts. They want you to say, hey, zeros always occur on the x-axis. That's why they're called x-intercepts. So, yes, I have 1 at 0. I have 1 at 1. I'll call that a 0. 1 at a negative 1, so let me put my zeros there. And I have 1 at square root of 2. Now, good gracious, what's a square root of 2? Believe it or not, it's bigger than 1. Just a little bigger than 1. So I have another one right about here, and that's a square root of 2. But I also have 1 over here on this side. That's a negative square root of 2. Well, if you think about all those dots, what do they have in common? The y value is 0. So they're going to want you to write them out like this. 0, 0. 1, 0, all the y's are 0, negative 1, 0. We continue down here. Square root of 2, 0. Final is negative square root of 2, 0. So that's a good thing to think about. These are what the answers are. This is basically where are they on the grid. Where are they? Go ahead and check your answers. I hope they're right. Oh, yeah, and look at, I like this. They were thinking what I was thinking. Go ahead and plot them in there. So they plot them a little better than I did because they got a grid. And if you were to graph it, you would find out that you have, look at these turns. Look at this, 1 turn. Am I even drawing? A 2 turn, 3 turn, 4 turn, 5 turn. So you always have 1 turn less than the highest degree. So since it was a 6 degree, 5 turns make sense because 6 minus 1 is 5. 5 turns. Also, we're going to find out, well, we should already have learned it, that both sides go up because we learned earlier that if you're looking at the highest degree and it's even, they're both either going to go up or they're both going to go down. That just depends on the coefficient in front. Well, 1 is positive, so that's why it goes up. And that's exactly the picture. Beautiful. I love how this reviews what we've already learned. Okay. Example. Now I got 3 examples here in a row. And so I'm going to work them out first, if I can. Then we'll look at the answers. This is to save some time. Find the x-intercepts. Well, that's what we just got done doing. A new kind of problem, guys. I'm pretty sure you've never learned how to factor a cubic. Maybe if you had college algebra last year, you might have. But I'm looking at 1, 2, 3, 4 terms. And it's hard to factor a cubic. But there is a method that I've learned that if you could do it by grouping, like pick 2 of them, put them together, and the other 2 together and treat them separately and see if it works. I'm just going to treat it like this is a couple and this is a couple. See what happens. You could also move them around and pair them differently if this doesn't work. But if I take these 2 together, I might be able to say I could factor out the highest degree is x squared there. The lowest degree is x squared. So let's see what happens if I factor out of the x squared out of these 2. If I take x squared out of x cubed, I'm left with 1 x's. Then I do a minus, bring down the minus. If I take out an x squared, I'm taking out an x squared out of 5x squared, I'm left with a minus 5. Okay, so it's x squared times this. Now I come over here to the next side, and I'm going to pretend these 2 things go together. And so I'm going to put a plus sign right here. Say, what could I factor out of these 2? Well, I can't factor an x out of both, and I can't factor out a 5. But what I could do is factor out a negative, maybe. See what happens. If I pull a negative out of a negative x, guess what we're left? X. If I pull a negative out of a 5, well, then all that does is change the sign of 5 to a minus 5. And I go, oh, thank goodness. That actually worked pretty good. But let me rewrite this a bit so you can see something what I was thinking. X squared times x minus 5 plus minus really means minus. I don't need to write the 1. X minus 5. Well, if you look carefully, now this is why it's hard. This is so different than anything you've done. I have 2 different sets. Both of them have an x minus 5. See that? X minus 5, x minus 5. I will factor out an x minus 5. What's left in my next set? I have an x squared minus a what? Oh, there was that minus 1, remember? Minus 1. Yay, there's my f of x equals to x minus 5 times x squared minus 1. It's factored, believe it or not. It really is factored. I'm excited. So now I take each of these, x minus 5 set equal to 0. I take x squared minus 1 set equal to 0. I add 5 to both sides. X is 5. I don't square root it because that's just a linear term. Now, this one is a quadratic term. When I add 1 to both sides, I get x squared equals to 1. On this one, I have to square root both sides, giving me x equals to a positive 1 and a negative 1. Does it make sense I could have 3 zeros? 1, 2, 3. It sure does. It makes sense. And remember what a cubic looks like. They're probably going to show me in my solution maybe. Cubic looks like that. If it's a positive cubic, and it is, this is positive, it starts from the bottom, goes up, has a turn, so technically it looks like there could be 2 turns. 1 turn, second turn. Sometimes those turns, though, blend in so well you can't count 2. So what we say, it has at most 2 turns. They could have just 1 turn depending on how it looks on the calculator. But anyway, those are the answers. Those are my x-intercepts. They're also called zeros, remember? Those are my x-intercepts. They're also called zeros. We'll check the answer after. The only thing I didn't do is put in their ordered pairs. But if I forget to do that, bear with me because you'll remember it. Remember, 0 means y is 0. So 5, 0, 1, 0, negative 1, 0. Find the y-intercept and the x-intercepts. Okay, well, that's interesting. Y-intercept happens when x is 0. X-intercepts happen when y is 0. And you're saying, was y equal to 0 in this first one? It sure was. I just didn't write it. I wrote f of x equals this, and then I factored it. But in reality, I let the whole thing equal to 0 is what happened when I did this factoring. So it is equal to 0 because I only dealt with this term and this term. So I was ignoring the 0. Right here I said x minus 5 is 0, so I was setting it equal to 0. Anyway, let's try this one. Y-intercept is when the x is 0, so that's very easy. So let's do the y-intercept first. X's are 0. X's will be 0. Here goes. Y-intercept. X's will be 0. So this becomes y. So my y will be equal to a 0 minus 2 squared times 2 times 0 plus 3. 0 minus 2 is a negative 2. I've got to square it. And then a 2 times 0 is a 0. 0 plus 3 is 3. Negative 2 squared is a positive 4. Times the 3 is a 12. So that point would be, if the x is 0, 0, 12. X-intercepts means the y has to be 0, so that means this becomes 0. So 0 equals to x minus 2 all squared, 2x plus 3 not squared. These are factored. So what happens is I write out x minus 2 squared does equal to 0. But when you square root both sides, you still get a 0. So x minus 2 is 0. That means x is a 2. That's one of my zeros. That's one of my x-intercepts. This one here, 2x plus 3 now set equal to 0. So x must be a negative 3 halves. Okay. Ordered pairs. Let's just be consistent. That means the y is 0. So when I write this one out, I have a 2, 0, and I have a negative 3 halves, 0. And let's do the last one. Find the x and y intercepts of this polynomial using a graph. All right, so unfortunately, you would have to pick up a calculator to graph this. They're telling you that, they're giving you a hint that this might be a cubic, but I bet you it doesn't factor. And I'm looking at it really quick to see if they're right. No matter how I pair this off, if I factored out an x squared here, I would still have an x plus 4. And then this one has nothing, x minus 6. Notice how there's nothing similar? So it probably doesn't factor. I could play around and try to repair them off with different things. It'll never factor. So we'll just pretend that I never even tested it. They want us to use a graph. So I'm going to have to use my calculator. What I'm going to do is I'm going to graph it on my calculator. And if you have the desire to graph it before I come back, that'd be great. I'm going to pause it, go to my calculator. Okay, I'm going to paste my graph here. Okay, I don't know how much of it you saw me putting there, but there's my picture. And so if we're looking for the x-intercepts of this polynomial, hopefully I keyed it in right. You can, it doesn't show the function on the picture, but I think I did do the x cubed plus 4x squared plus x minus 6. And if I didn't do it, well, then we're going to pretend this was the, the graph. So let me put a color that I can probably see on this black screen here. Where are my x-intercepts? One is right here, one is right here, one is right here. I think I keyed it in right because it's too perfect, okay? And boy, there might have been there is a way to factor this that you haven't been taught yet. But just normal factoring was probably going to be hard. So if you can't factor, you can always graph it and see. But then this one stands out really good. I do believe I have one at every 2 tick marks is 1, so that's a 1 comma 0. Then this one that's a 2, 3, 4. That's a negative 4 comma 0. And then that would be, or I'm actually wrong. Yeah, that would be, I was wrong. That's a 1, that's negative 2. Let me fix that. Negative 2, comma 0. That one is a negative 3, comma 0. Those are my x-intercepts based on a graph. Now, if they don't cross at a beautiful intersection, you would have to use your calculator to look for the x-intercepts. You go to Analyze Graph, find the zeros, and you can actually move your thing around and find exactly what those values are. That's all I'm going to do with this one right now. Okay. So, can I leave it all up here? Yeah, that's fine. Move on. Oh, you have another example. Oh, I already did this when I was making my lecture notes. I use Google to graph instead of using my calculator. Well, I just did it with my calculator, which is better because look at this one came from, that top one came from just in Google. I just told it to graph this picture. But I didn't like it. I didn't like that it didn't give you much help to find the zeros. So then I used a different program online, and yeah, it's a lot better. And it looks like it's my answers. I think I was going there. I was going here, and I was going here. They put other dots to represent something else. So that's talking about that program's labeled the y-intercept as well, and it also labeled a maximum value, but I only cared about the zeros. So anyway, you can use a lot of ways to graph it. If you're on the fly and you want to grab a calculator, you could go to Google real fast and get a picture, but it won't always be correct. Wow, they wrote a lot. I think, yeah, okay, that's that one that I had. Yeah, that was that, that was that cubic that I could factor. Yeah, look, it did the same way as me. Yeah, there's a y-intercept up there at 12. Yep, I think I got it. There's that one. Let's see. How did they do it? Wow, they did some fancy stuff to factor it. Holy cow. I wasn't interested in that. Oh, I think they graphed it first and they did something. I like my method better. Okay, moving on. Identify zeros and their multiplicities. All right, I hinted to this already. Look at this picture here. This equation, it makes that graph. Now, if you look at that equation, I can find a zero here. And that looks like a line, doesn't it? Look like a line? That means it's multiplicity of 1. Multiplicity of 1. I should put of 1 here so you can see it. What was the answer? That looks to me like a -3. So let me put -3. So that ordered pair would be -3, 0. And there's only one of those. If you look over here, this piece looks like a quadratic. When it bounces off, it means there's 2 of them. Could also mean 4, could also mean 6, could also mean 8. But most likely it's 2 of them. So it's multiplicity of 2 of, that's a 2, 0, so 2, 0. So technically there are 2 zeros there. There are 2 2s. That's why it bounced off. There are 2 2s. But there's another place here that may not be as clear. If it is clear as mud. There's another 0 here. But see how it rides the axis for a while? And then it goes up, rides, and then goes up? That had to be an odd degree term. So odd means a 1, a 3, a 5, a 7. I'm going to use the 3. Just because, what are the odds that they would have it multiplicity of 3? And that would be -1, 0. So if I add those up, I have 2 here, 3 here, that's 5. Then I have 1 over here. This one was 6. Now, does that look like it could be a 6 degree? Without multiplying it all out and do FOIL, first, outer, inner, last, take that answer and distribute it. Oh, look at this. You got 3 of these here. No, you can't even do what I just said. Rewind. Because there's a square here. Okay. So I'm going to give you a shortcut. Let me just reverse time. I feel like I'm Cher singing, if you could turn back time. I just did. I turned back time, just like Cher did. I'm going to give you a secret. There's a first degree here. That means there's only going to be this x to the first. There's a square here. If you FOIL this out, it's going to be an x squared. Here, if you do the x plus 1 times the x plus 1 times an x plus 1, who wants to do that? Nobody. That would give you x times x times x. That gives you an x cubed. So that gives you 3, 4, 5, 6. This would be an x to the 6 because all the x's have a 1 in front. So it's an x to the 6 is your highest. It makes sense that I have 6 zeros. Ta-da. That wasn't bad. The key word is multiplicities. If it crosses it, then it has to be a 1 or a 3 or a 5. Usually go for the 3 or the 1. If it just crosses it nice and pretty, go for 1. But if you see a writing, go for 3. If it hits it and bounces off, go for 2. This one goes straight through nice and pretty, so it's just a 1. This one rides it, so I went to the 3. That's what I did. What's down here? Oh, they're just showing you. If it crosses it, you just got multiplicity of 1. If it bounces off, multiplicity of 2. Rides the axis, go with multiplicity of 3. That's what they're saying. There. Here, that's written right here. The 0 is 0, and there's one of them. The 0 is still 0 because it touches at 0, 0, but there's 2 of them. The answer is still 0, but there's 3 of them. Okay? Is that the one I just did? No. Well, yes, it is. The same one I just did. Not sure why I have it here again. Move on. Oh, there's the answer. I'll let you pause it and read it if you want. End behavior. You kind of already understood this. If your leading coefficient, look at your polynomial here. Some number, x to some exponent, some number, x to some other exponent 1 degree less than the one over here. This one was n, this has to be n minus 1. You always put them in order from highest to lowest, right? Until you get all the way to a number, and it's really x to the 0. Because you had x to the 1 here, x to the 0. X to 0 just means that it doesn't really have to be shown. So this is a polynomial that's in order, okay? In standard form. Remember, it's in order. So we always look for the leading term. And it should be the highest exponent, okay? So what we look at that and we say, if we're looking at, I'm going to make something up. F of x, I'm going to put x to the, I'm going to put a 2x to the 4th, okay? Since the front number, coefficient, is greater than 0, and it's an even degree, 4 is even, they both go up, but it's possible they both go down if your leading coefficient was negative. That would be f of x is negative 2x to the 4. So you either both go up, both go down. If it's an even exponent, the highest one's even, they do the same thing. If the exponent is odd, like it's a 1, which is just a line, that's silly to say it, but a 1, a 3, a 5, a 7, and so forth, one side goes up and one side goes down. How do I know? Well, I'm looking at this one. I'm going to write f of x is a 4x to the 5th power. So it's an odd degree. Coefficient is positive. That means greater than 0. That means it has to start from the bottom and go up this way. And then it'll cross somewhere, and then it's going to still keep going up. So one side goes, left goes down, right goes up. Now, if we change it, oh, and by the way, I'll talk about how we write it out. If we change it to f of x is a negative 2x to the 3rd, let's say, that's still odd, but now that's negative, less than 0. It flips this shape here. Instead of rising from the left, it falls from the left. It flips it upside down. Well, we had that. Remember when you put a negative in front of a function, it flips it upside down? Well, that just flipped upside down. Now, look how we write our answers. as x goes to infinity, the y values go to infinity. That means as x goes to the right, y goes up. As x goes to the left, that means negative infinity. That's what's happening. F of x goes up. I should say infinity, to be honest with you. Why? It goes up forever, so we just say infinity. So as x goes to the right forever, the function goes up forever. As x goes to the left forever, the function goes down forever. As x goes left forever, the function goes down forever. That's how you read those. If it is negative leading coefficient and the exponent is even, as x goes to the right forever, the y values go down forever. As x goes to the left forever, the function goes down forever. Okay? If you have any questions, just ask me. So here is a problem that wasn't really an example in the book, but they wrote it as the big paragraph, and I just pulled out the equation and I wrote out the graph. It's just to show you what's happening here. Because we're talking about turning points now. Remember what I told you about turning points? You can predict them to be one less than the highest power. So these are in order, 4, 3, 2, 1. So they're 4 minus 3. I'm sorry, I'm thinking of the answer. Rewind time. 4 minus 1 is 3. 3 turning points. And if you look at the graph, turning point happens when it went from decreasing to increasing. That's a turning point. From increasing to decreasing. It's always from left to right. Turning point. From decreasing to increasing. Turning point. 3 turning points. I think they probably told you the same definition in this box right here. A turning point is a point on the graph where the graph changes from increasing to decreasing, rising to falling, or decreasing to increasing means falling to rising. A polynomial of degree n will have at most n minus 1 turning points. That means it can have less. But for the sake of argument, the highest it can have is n minus 1. All right, example 7. Really simple here. Just identify the highest degree. This is tricking you because the 3 goes before the 5, and that tricks you. A lot of people are going to say, oh, good, 3 is the highest. No, they didn't put it in order. 5 is the highest. 5 minus 1 would be 4. At most 4 turning points. That's why find the maximum number of turning points. They know that there could be less, but maximum would be 4. The second one, unfortunately, they didn't multiply it all out. It's in factored form, but I gave you a secret not too long ago that this x, the highest, there's a 1 in front, the highest that this 1x can become is x to the second power, right? Over here, the highest that this factor could be is also x to the second power. Well, if you were to multiply those together, your highest power will be the 4th degree. There's no way that any other term will be higher. Maybe the answer is going to show us where they did a lot of extra work. I'm telling you, you don't need to do all that work. If you're just looking for the highest power, it's not cheating, it's common sense. X times x can only be an x squared. If you had 2 of those, 2x squared times 2x squared, which is what would happen. Well, actually, it's not being squared. It's just 2x squared. It doesn't get squared. stays at 2x squared. So x squared times 2x squared would only be a 2x to the fourth. If I write 2x to the fourth, big deal, still x to the fourth. So at most, 4 minus 1 is 3 turning points. We can look at the answer and see what it says. I can't think, well, yeah, they sometimes do extra work. Did they? Let's see. Yeah, they're working it out. They're doing, actually, no, they didn't. They kind of did the same thing as me. Same answer. It's probably the same. I'm proud of them. Graphs of polynomials. Now, I'm just going to give you a polynomial and say graph it. So we look at our steps here. What did I write at the top here? Did I write anything I want to know? We could talk about when you're graphing, you use your multiplicities, you use your end behavior, and you use your turning points. And you also use zeros. Do they say zeros? Multiplicity. Well, multiplicities has to do with zeros. So, yeah, we're talking about multiplicities. So how do we do it? Find all intercepts. That means your x's and your y-intercepts. Use symmetry. This is probably a little bit I don't pay attention to too much, but I do use multiplicities. That way I know, does it cross the axis or will it be bouncing off? Determine the end behavior based on those leading coefficients and the highest powers. Use the end behavior to tell you how it's going to go. So yeah, this is what we're doing. Look at the turning points, and then you can always use technology to check it. Well, technology, your graphing calculator will give you the best answer. So let's see if we can do this one. Sketching the graph of a polynomial. I am not going to multiply it all together to see what it really is. I will see what the highest power will be. X being squared will be an x squared. Yes, there's a negative 2 in front, so that's going to be multiplied by it. This x minus 5 is a 1x. That's the highest it's going to be, so it's times a 1x. So your highest power and the leading coefficient, this is cool. See, I'm giving you 2 for the price of 1. Negative 2 times 1 is a negative 2x cubed. That tells me a lot. I can tell you right now that my graph's going to start at the top. It's going to come down, it's going to cross the axis, and it's going to keep going down. Ta-da! It looks like that. Because when your cubic is negative, it starts at the top and falls all the way down. And since it's a cubic, there could be 2 turning points. At most, 2 turning points. At most, actually it's not even at most 3 real zeros. 3 real zeros. But it is possible to only have 1 real zero. It really is. For instance, y equals x cubed only has 1 real zero because it starts at the bottom, comes up, touches the 0, and goes back up. 1 real zero. But it has 3 zeros. I don't want to hurt your feelings, but they're just not real. They're going to be imaginary. We're not doing imaginary today. Aren't you glad? So there's my rough graph, but we can do better. Let's put it on a grid. We know that my zeros will be x plus 3 set equal to 0. X can be a negative 3. But there's a square here, so it's multiplicity of 2. Bx minus 5 set equal to 0. X is 5. Is a multiplicity of 1, since there's no power out here. And plus, it's not an x squared in there. That would change it too, but multiplicity of 1. Well, there you go. I have 3. I have 2 and 1, means 3 zeros. So x is negative 3. 1, 2, 3 has to be here. X equals to 5. 1, 2, 3, 4, 5 has to be here. But that doesn't tell me. So I do know, like I said, it's probably falling from up here. So it's going up that way, so it's falling down this way. And it has to hit that 0. But what am I missing? I don't have the y-intercept. So let's calculate the y-intercept. Remember what that means? X has to be 0. So let me call that y and say y has to be a negative 2 times a 0 plus 3. My pen's not running again. 0 plus 3 all squared times the x minus 5. So the x becomes 0 minus 5. So that turns into a negative 2 times a 0 plus 3 is a 3, and I'm going to have to square it, times a 0 minus 5, not squared, just a negative 5. That turns into a negative 2 times 3 squared is 9 times a negative 5. That turns into a negative 18 times a negative 5. That 18 doesn't look good. Let me do that. 18 times 5, and that's 40, 90, positive 90. Wow, that's not exciting. It's gotta, let me make my axis a little taller here. Boop, 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 boop. Boop, 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 boop. Up here to 90, way up there. Okay, so I have everything I need now. If I know that it falls from the left, and I know it has to hit this negative 3, 0, and because it was a multiplicity of 2, it's even, so it has to bounce up. My guess is it has to at least bounce up so it can cross this point here. Has to cross the y-intercept. Now, I don't know if it goes through it and goes right down, or does it go through it? Not really sure. But I know it has to come back down because it has to hit this 0. So somewhere it comes down to cross that 0. Both zeros have to be crossed, and it has to come straight through it because it's multiplicity of 1. So it's going to, odd number means it has to cross it, so it's going to continue down. Well, that's exactly what I said was my end behavior. As x approaches negative infinity, that's a bad, approaches a negative infinity, f of x is approaching infinity, up forever. As x approaches to the right forever, f of x has to approach negative infinity. So I like my picture, and I'm going to say that's my graph. Is it perfect? Probably not. But it has everything you need. It has where it crosses the y-intercept here. It has 1 turn, 2 turns, which is the most that a cubic can have. Okay, let's see what they did. And I remember making the slides for this. Their explanation was a lot of steps. So I'm just going to show it to you, and we'll look at the very end. They did the end behavior exactly. You can read it and see what it says. It actually already found the y-intercept because that is the easiest thing to do. I think I did it last. It doesn't matter. We're at the same place, 90. And so move on here. They added that, and then they added the 2 x-intercepts. Looks very familiar to my picture. I can see it coming down. It's probably going to bounce off here. It's got to go over here. It's got to come back down to the other 0 they have marked over here. I don't know if they marked it. Don't know. But we'll see. Next slide. They probably did another step. There they are. Now they made them both. There's both of the x-intercepts, and there's their picture. Their scaling is different. Their 90 is not very high. You know, like 1, 2, 3 tick marks. They counted by 30, cheaters. But it's the same idea. goes through it, has to come back down. Yeah, I like what I did. Hope you did too. Let me know in a comment if you liked it. Now, intermediate value theorem. We call this IVT. Basically, I call it the in-between theorem. All it does is it tells us if there are any real zeros. So do I want to read all this? Let's see. Let me try to abbreviate what they're saying. They're saying that if you have, like on a number line, we have a graph, and we have something, an A number here, some number, that's an X, and a B number here. So, and we know in this case, for instance, A is less than B. So that is true. And if you're graphing something and you plug in f of A, and f of A is, let's say, greater than 1 or greater than 0, all that means is you have a value up here somewhere. And then you look at f of B, and you find out that it's not positive, that it is less than 0. Well, that means it's down here. Well, what does that mean then? That means you have to have 1 0, at least 1 0. Tell me why I have to have 1 0. How do you go from here to here without crossing the x-axis at least one time? That just proves you have to have a 0. I don't know what it is. It could be x equals to pi. That would be very hard to find. It could be x equals to the square root of 5. That would be hard to find. It could be x equals to 3. It just doesn't matter. But the answer has to be between, I'm going to do this, that between A and B has to be the answer. X has to be in there somewhere between A and B. Because this value is f of B, that's the y value. This is f of A. So the y value has to be between these two, and the x value has to be between these two. I hope that makes a little bit of sense. And so all we use it for is to try to say, is there going to be a 0? Maybe they worded this simpler. Let f be a polynomial function over an interval a to b. Notice closed intervals? That means there were points, like I made. And they gave it a weird name here. Bolzano's theorem. I have never seen it as Bolzano. We call it the intermediate value theorem. I guess Bolzano invented it. He states that if f of A and f of B have opposite signs, remember I said one was positive, one was negative, then you know that there has to be at least a value called C, which is the 0, that has to be between A and B, where f of C has to be 0. That means that's a 0. So I'm looking at this one here, example 9. Show that the function f of x equals x cubed minus 5x squared plus 3x plus 6 has at least 2 zeros. Oh, they want me to find at least 2. And it says between 1 and 4. Between x is 1 and x equals to 4. Well, let's just make a table. Here are my x's. Between 1 and 4. So I got 1, 2, 3, 4. Let's see what f of x will be. Let's just see what's happening. Because we know f of 1 and 4 has to be on the graph. So let me plug in the 1. So I hope you can do it with me in the head. If I plug in a 1, 1 cubed is 1. And I plug a 1 for squared, that gives me a 1 times minus 5. 3 times 1 is 3, plus 6. If I did it right, I have 1 minus 5, that's a negative 4. Negative 4 plus 3 is a negative 1. Negative 1 plus 6 is 5. I think it's 5. I hope it's 5. Let me plug in the 4. That's going to be a little harder, okay? I'll do it over here. 4 cubed, oh my gosh, 4 times 4 is 16 times 4, 64. Minus 5 times 4 squared is 16. 5 times 16, 50, 60, 80. Minus 80. 3 times 4 is 12, plus 12, plus 6. So 64 minus 80 is a negative 16 plus, what was that one? 12 plus 12 plus 6. That's going to be a negative 4 plus 6, 2. If I did it right, it's a 2. So those are my endpoints. So all I know, I'm looking at 2 endpoints. At 1, I go up to 5. And at 4, I go up to 2. So right now, that doesn't prove anything. Those 2 endpoints, they're both positive. So let's check what happened to 2. So f of 2. I'm going to do f of 2. 2 cubed minus 5 times 2 squared plus 3 times 2 plus 6. That's 8 minus, that's 5 times 4, it's minus 20, plus 3 times 2, that's plus 6, plus 6. That's negative 12, plus 12, 0, 0. So at 2, it goes to 0. Well, that's one of the zeros. Hello, found one. And I don't have to do the 3, because 3 is going to be here. It has to go, it doesn't even really matter what the 3 is. If I have to go back, well, I mean, 3 is going to have to probably be down here. I guess I better check it. Let's check it. Let's do f of 3. If I don't, it has to be negative. It has to go down, so it has to be down here. Let's check it. F of 3 will be a 3 cubed minus 5 times 3 squared plus 3 times 3 minus 6. I hope it works. It's always a chance. Here it goes. 3 times 3 times 3 is 27. Minus 5 times 9 is 45. Plus 3 times 3 is 6. I'm sorry, 9. Minus 6. So I didn't. That's 27 minus 45 plus 3. 27 minus 45. Well, let's do this. 27, 28, 29, 30. 30 minus 45 is negative 15. Okay. So I hope I'm right. If I'm wrong, I'm not redoing it. But I got a negative 15, so it's down here. So yes, to go from here to here, it has to cross again. So I think it's proven. At least 2. All right? You can check it and see it. I don't know if my math is always right. It doesn't look like I did the math right. If you find a mistake, let me know. But it still says negative. I'm going to run with it. Is that the same problem? It's the same problem. They're just showing you that I had a point here, and then I had a 0, so that's 1, and then I had a negative number, has to go back up to where the 5 was, so yeah, they're just showing you the same thing. What was this one? It's a try it problem, and I'm going to leave that for you. And writing formulas for polynomial functions. So what are we doing here? Given a polynomial function, I'm reading the how-to. Identify, okay, you're looking at a picture, I think. Identify your x-intercepts. Identify the factors that go with those zeros. Look at the behavior so you know what the front number has to be. You know what the highest power could be. Find the least degree polynomial you can have. Use a test point here to find missing things. So let's see what we're going to do here. Example 1. Here's this picture. So we're almost done. I know I have a 0 here. So x has to be a negative 3. That gives me, if I'm doing a polynomial, p of x has to have an x plus 3. You know what, it's drawing big because I've zoomed in. Let me just erase it and do it a little nicer. X plus 3 has to have an x plus 3. Why? Because if x is a negative 3, move the negative 3 over, that gives you x plus 3 has to be 0. So I'm not going to do that for every one. Then I have another 0 here. X is 2. But since it bounces off, there's 2 of them. Multiplicity of 2. So I have an x minus 2, and there's 2 of them. Then I have 1 here, it's a 5. X is 5, so x minus 5, and it goes straight through. So we're going to call it, the lowest value would be x minus 5 all to the first power. So there's your function. And the only thing I'm missing in here is there should be a number in front that I don't know what it is. I can't guarantee that because there's a 1 here, 1 here, 1 here, that the front number is a 1. So you have to say there is a missing number. Well, how am I going to solve for that missing number? Find a point that I agree with on here. Look at here. There's a y-intercept right here. It's a beautiful y-intercept. That y-intercept has a value of 0, negative 2. So I'm going to use this point to say the x is 0 and the y is a negative 2. So the negative 2 goes here, and the x is 0 will go here, and it's going to go here. So I'm going to write that out. Negative 2 equals to sum a times 0 plus 3, that's 3, times 0 minus 2, that's a negative 2, squared. Negative 2 equals 2, and a times a 3 times a 4, because a negative times a negative is positive. Negative 2 equals 12a. Divide both sides by 12. That a has to be a negative 2 over 12, which is negative 1 over 6. Now, did they tell me I had to write the formula for the polynomial function? I'm going to be lazy. I'm just going to say my polynomial function has to be a negative 1 over 6 times an x plus 3 times an x minus 2 squared. Oop, did I forget to do the x? I forgot to do the x minus 5. Sorry. There is a minus 5 here. 0 minus 5. Oops. Negative 5. So I forgot to do that. 3 times 4 times a negative 5. So it's not going to be a 12a. It's going to be 12 times negative 60a. I'm sorry. Negative 60a divided by a negative 60. So it's negative 1 over 30. Yikes. That's an ugly fraction in front. Negative 1 over 30. Let's double check that. You know what I didn't do? I had to divide by the there was a negative 2 here. So it was, A is a negative 2 divided by the negative. So this was a negative 2 divided by a negative 60. They're both negative. So if they're both negative, it's just positive 1 over 30. So it's not negative. Okay. Double check. Okay. There's my answer. I'm not multiply that all out. I'm too lazy. Let's see what they have. There's the picture like we had. Looks like they set it up the same way. Yes, it is a 1 over 30 in front. And, oh, they didn't multiply it out either. They did what I did. They're cheaters, too. You don't need to multiply it out. Calculator will do it either way. And here's a try it just for you. I'm going to save it for you this time. I might use those try-its on your final exam. Anything else? Yeah, there's that solution to there's this one, local. And I'm going to have you just read these slides. And we did max and mins before. We've already done them. Max and mins. The highest mountains, the lowest valleys are local. And if there's nothing else on the whole graph that's higher, we call it the global, the absolute max. So I'm going to let you just finish that up yourself. Pause it, read it, do it. Tentatively, I have a homework assignment, and it's 1 through 5 all on the first page. The other pages are multiples of 5. So you're not doing that many problems. So there's your first page. All of those have to be done. Multiples of 5. So that would have been, the first one you'd be doing would be 10. Then you'd be doing 15. Then you would be doing 20. Then you'd be doing 25 if it's there. 25. Then you'd be doing 30. You get the hint, right? So you're not doing that many of each section. Keep going. Multiples of 5. You can figure it out. Still multiples of 5. Still multiples of 5. Still multiples of 5. And I think this is the last page, so the highest you're going is to 65. So the least you'd be doing would be 13 problems, but I think there's 5 you're doing. You're doing like 18 problems, I think. Any questions, let me know.